You're sitting at your computer right now, with terabytes of storage at your fingertips. You can save a high-definition movie in seconds, back up thousands of photos to the cloud, and carry more data in your pocket than entire corporations could store just decades ago. But this wasn't always the case. In fact, the journey to get here is one of the most fascinating stories in the history of technology. Today, we're going to travel through time, exploring how human beings went from storing information on physical objects to the lightning-fast solid-state drives that power our modern world. This isn't just a story about technology. It's a story about human ingenuity, the relentless pursuit of efficiency, and how the way we store information has fundamentally shaped the digital age we live in. But before we dive into floppy disks and hard drives, we need to understand where it all began. Because long before anyone dreamed of gigabytes or terabytes, humans were already grappling with a fundamental challenge. How do you store information in a way that machines can understand and process? The year was 1725, and a French textile manufacturer named Basile Buchin had a problem. Weaving complex patterns required incredible skill and time. Workers had to manually control each thread, making the process slow and prone to errors. But Buchin had an idea that would echo through the centuries. He created a system using perforated paper tape to control looms automatically. Holes in specific positions told the machine which threads to lift and which to leave down. This concept, using the presence or absence of holes to represent information, was revolutionary. It was binary thinking before anyone called it that. Each hole was either there or it wasn't, representing what we now call ones and zeros. Buchin probably never imagined that his textile innovation would become the foundation for how computers would store and process information for the next 3 centuries. Fast forward to 1890, and we meet Herman Hollerith, a statistician working on the United States Census. The 1880 census had taken nearly 8 years to complete by hand, and with the country's growing population, the 1890 census threatened to take even longer. Hollerith remembered Buchin's punch paper concept and adapted it for data processing. He created the Hollerith punch card system. Each card was roughly the size of a dollar bill, not by coincidence, but because that was a standard size that existing storage systems could handle. Information about each person was encoded as holes punched in specific positions on the card. Age, occupation, place of birth, all of it could be represented by the pattern of holes. But here's what made Hollerith's system brilliant. He didn't just store the data. He created machines that could read and sort these cards automatically. His tabulating machines could process information faster than any human ever could. The 1890 census was completed in just 2.5 years, saving the government millions of dollars and establishing punch cards as the dominant form of data storage for the next 8 decades. Think about that for a moment. Before Hollerith, data processing was entirely manual. After his innovation, machines could not only store information but manipulate it, sort it, and perform calculations with it. This was the birth of automated data processing, and punch cards were its first storage medium. As the 20th century progressed, punch cards became increasingly sophisticated. The standard IBM punch card, introduced in 1928, could hold 80 columns of data. Each column could represent a letter, number, or special character through a specific pattern of holes. A single card might contain information about an employee, a customer, or a financial transaction. By the 1950s and 1960s, punch cards were everywhere. Every major corporation relied on them. If you worked for a large company, your payroll information was on punch cards. If you had a bank account, your transactions were recorded on punch cards. If you went to university, your grades were stored on punch cards. The phrase, "do not fold, spindle, or mutilate," became part of the cultural lexicon because damaging a punch card could mean losing important data forever. But punch cards had significant limitations. Each card could only hold a small amount of information, about 80 characters. Processing large amounts of data meant handling thousands or even millions of cards. Storage rooms filled with carefully organized card files became a common sight in corporate America. And if you dropped a box of cards, you might spend hours getting them back in the right order. The cards were also vulnerable. They could be damaged by moisture, torn by mishandling, or destroyed by fire. More importantly, accessing data was slow. If you needed information from a specific card, you might have to search through thousands of others to find it. Despite these limitations, punch cards taught us crucial lessons about data storage that still apply today. They showed us the importance of standardization. The reason different companies could share data was because they used compatible card formats. They demonstrated the value of random access, the ability to go directly to a specific piece of information rather than reading through everything sequentially. But perhaps most importantly, punch cards established the fundamental principle that would drive storage innovation for decades: the need for higher capacity, faster access, and greater reliability. Around the same time that punch cards were becoming ubiquitous, another storage technology was quietly revolutionizing how we thought about data: magnetic tape. The concept emerged from audio recording technology, where magnetic tape was already being used to store sound. In 1951, the UNIVAC computer introduced the first magnetic tape system designed specifically for data storage. These early tapes were massive by today's standards, half an inch wide and up to 2,400 feet long, stored on reels that looked like oversized film reels. But they could hold far more information than punch cards, and they could be read much faster. The beauty of magnetic tape lay in its elegance. Instead of physical holes, information was stored as patterns of magnetic fields. A magnetized spot might represent a 1, while an unmagnetized spot represented a 0. This meant that data could be written, erased, and rewritten on the same tape multiple times, something impossible with punch cards. Magnetic tape also introduced us to sequential access storage. Unlike punch cards, which could be randomly shuffled and accessed, tape had to be read from beginning to end. If you wanted data from the middle of a tape, you had to wind through everything before it. This limitation would shape computing for decades, creating a clear distinction between sequential and random access storage that persists to this day. By the 1960s, magnetic tape had become the backbone of data storage for large computers. Massive tape libraries, with automated systems that could select and mount specific tapes, became common in corporate data centers. The image of spinning tape reels became synonymous with computing power. But we're still in the prehistory of personal computing here. These early storage technologies, punch cards and magnetic tape, required enormous, expensive machines operated by trained specialists. The idea that individuals might own their own computers with their own storage systems seemed as fantastical as personal spaceships. That was about to change. The late 1960s and early 1970s saw the convergence of several technologies that would make personal computing possible: smaller, more affordable processors, compact memory systems, and most importantly for our story, storage systems that could fit on a desk rather than filling an entire room. The stage was set for a revolution. Engineers and entrepreneurs around the world were working on the same challenge: how to create storage systems that were small enough, cheap enough, and reliable enough for individual users. They needed something with the capacity advantages of magnetic tape, but the accessibility of punch cards. They needed something that could store programs and data, but also allow users to easily share information between different computers. The solution they came up with would define personal computing for the next 2 decades. It would become so ubiquitous that billions of people would instantly recognize its distinctive square shape and metallic sliding door. It would survive format wars, technological upheavals, and the transition from hobbyist computers to mainstream adoption. That solution was the floppy disk, and its story begins in the laboratories of IBM in the late 1960s, where a team of engineers was working on a problem that seemed almost trivial: how to load software into computers more efficiently than using stacks of punch cards. They had no idea they were about to create an icon. The year was 1967, and David Noble was frustrated. Noble worked at IBM San Jose laboratory, and his team had been tasked with solving what seemed like a simple problem: how do you load microcode into IBM's new System/370 mainframe computers? At the time, this required feeding stacks of punch cards into card readers, a process that was not only time-consuming but also prone to errors. A single damaged card could corrupt the entire loading process. Noble's team needed something that could hold more data than punch cards, but was more portable and reliable than magnetic tape. They needed something that could be easily manufactured, shipped, and handled by computer operators. Most importantly, they needed something that would be cheap enough to be disposable if damaged. The solution they developed was revolutionary in its simplicity. They took the magnetic recording technology from tape and applied it to a flexible disc of magnetic material, enclosed in a protective square envelope. The disc could spin inside its envelope, allowing a read/write head to access any part of it without having to wind through everything sequentially like tape. It was random access storage in a portable, affordable package. They called it the floppy disk because, well, it was floppy. The original 8-inch discs were indeed flexible, and you could bend them slightly in your hands. But this apparent fragility was actually a feature, not a bug. The flexibility allowed the disk to conform to slight imperfections in the drive mechanism, ensuring better contact with the read/write heads. The first floppy disks could hold about 80 kilobytes of data, roughly equivalent to 1,000 punch cards. That might seem laughably small today, but in 1971, when IBM announced the first commercial floppy disk drive, it represented a massive leap forward in portable storage capacity. But IBM's marketing department initially missed the bigger picture. They positioned the floppy disk as a specialized tool for mainframe computer operators. The idea that these disks might become a standard storage medium for smaller computers that didn't even exist yet, wasn't on their radar. That vision would come from elsewhere. As the 1970s progressed, a new generation of computer enthusiasts and entrepreneurs began dreaming of machines that individuals could own and operate. The Altair 8800, launched in 1975, is often credited as the first commercially successful personal computer. But the Altair had a problem. It had no permanent storage. Every time you turned it off, any programs or data you'd created simply disappeared. Early Altair users had to load their programs by manually flipping switches on the front panel, a process that could take hours for complex software. Some users resorted to cassette tapes for storage, but tape was slow and unreliable. What they needed was something with the random access capabilities of magnetic disks, but affordable enough for hobbyists. Enter the floppy disk. By the mid-1970s, several companies were working on smaller, cheaper floppy disk drives that could be integrated into personal computers. The most successful of these was Shugart Associates, founded by Alan Shugart, who had previously worked on IBM's original floppy disk project. Shugart's breakthrough was recognizing that personal computers didn't need the industrial-grade reliability of mainframe peripherals. By simplifying the mechanism and accepting slightly lower reliability, they could dramatically reduce the cost. In 1976, Shugart introduced the 5.25-inch floppy disk drive. Smaller, cheaper, and perfect for the emerging personal computer market. The 5.25-inch floppy wasn't just a scaled-down version of the 8-inch disk. It represented a fundamental shift in how we thought about computer storage. For the first time, storage became truly personal. You could own your programs and data in a tangible, physical form. You could share software by literally handing someone a disk. You could organize your digital life by organizing physical objects. The early 5.25-inch disks could hold about 160 kilobytes of data, roughly 2,000 pages of text. But capacity wasn't their main advantage. Their real power was accessibility. For the first time, computer users didn't need to rely on expensive hard drives or slow tape systems. They could store and retrieve their data quickly and affordably. The impact was immediate and transformative. The Apple II, launched in 1977, was one of the first personal computers to integrate floppy disk storage as a standard option rather than an expensive add-on. Suddenly, personal computers became practical for real work. You could create a document, save it to a floppy disk, and come back to it later. You could buy software on floppy disks and install it on your computer. You could back up important data by copying it to additional disks. But the real revolution came with the concept of software distribution. Before floppy disks, sharing software meant sharing source code that users would have to type in manually. With floppies, software could be distributed as finished programs. This gave birth to the commercial software industry as we know it. Companies like VisiCorp, which created VisiCalc, the first spreadsheet program, built their entire business model around floppy disk distribution. You could walk into a computer store, buy VisiCalc on a floppy disk for $200, take it home, and immediately start using sophisticated business software on your personal computer. This had never been possible before. The 5.25-inch floppy also established many of the conventions that would define personal computing for decades. The concept of saving a document to disk became a fundamental metaphor. The floppy disk icon, representing the save function, became so universal that it persisted long after actual floppy disks had disappeared from most computers. But 5.25-inch floppies had their limitations. The large, thin disks were fragile and easily damaged. The protective envelope was simple cardboard and plastic, offering minimal protection against dust, moisture, or physical damage. The exposed recording surface could be accidentally touched, corrupted by magnetic fields, or damaged by improper insertion into the drive. Storage capacity was also becoming a constraint. As software became more sophisticated, programs grew larger. Early word processors might fit on a single floppy, but by the early 1980s, complex applications required multiple disks. Installing software meant swapping disks in and out of the drive, sometimes dozens of times for a single installation. The personal computer industry needed something better, higher capacity, more reliable, and more convenient to use. The answer came from Sony, a company better known for consumer electronics than computer peripherals. In 1982, Sony introduced the 3.5-inch floppy disk, and it was a masterpiece of engineering design. Unlike its larger predecessors, the 3.5-inch disc came in a rigid plastic case with a sliding metal door that automatically opened when inserted into a drive. The disc itself was better protected, and the mechanism was more precise, allowing for higher data density. The initial capacity of 3.5-inch discs was 400 kilobytes, more than double that of 5.25-inch discs, despite being physically smaller. But the real advantages were in usability and reliability. The hard plastic case meant you could throw 3.5-inch discs in a bag without worrying about bending them. The sliding metal door protected the magnetic surface from dust and fingerprints. The improved precision allowed for more reliable reading and writing. But adoption wasn't immediate. The computer industry in the early 1980s was fragmented, with different manufacturers pursuing different storage strategies. IBM was still pushing 5.25-inch discs for their PC line. Apple was experimenting with their own proprietary disk formats. Many manufacturers were waiting to see which format would become the standard. The turning point came in 1984 with the launch of the Apple Macintosh. Apple made a bold decision to adopt the 3.5-inch format exclusively, betting that its advantages would overcome the higher initial cost. The Macintosh's 3.5-inch drive became part of its identity. Small, elegant, and user-friendly, just like the computer itself. More importantly, Apple worked with Sony to increase the capacity of 3.5-inch discs to 800 kilobytes, then later to 1.44 megabytes. This higher capacity made the format increasingly attractive to software developers and users alike. By the late 1980s, most personal computer manufacturers had adopted 3.5-inch drives as their standard floppy format. The 1.44 megabyte 3.5-inch floppy became the defining storage medium of the late 1980s and early 1990s. It was large enough to hold substantial programs and documents, small enough to be convenient, and reliable enough for everyday use. For millions of people, the distinctive click of inserting a floppy disk and the whir of the drive spinning up became the sounds of computing. Floppy disks also created entirely new categories of social and economic activity. Software piracy, while illegal, flourished as people copied and shared disks. The phrase sneakernet, transferring data by physically carrying storage media, entered the technology vocabulary. Computer stores devoted entire aisles to boxes of blank floppy disks. Office supply companies added disk storage cases to their catalogs. But perhaps most importantly, floppy disks democratized computing. They made it possible for individuals to own, control, and share their digital creations in a tangible way. Your data lived on physical objects that you could hold, label, and organize. You could loan a disk to a friend, make backup copies, or store important data in a safe deposit box. This physicality created a different relationship with data than what we have today. When your work existed on floppy disks, you were acutely aware of storage limitations. You learned to be efficient, to organize your files carefully, and to make strategic decisions about what to keep and what to delete. The constraint of limited capacity forced creativity and discipline. Floppy disks also established the fundamental economics of removable storage that would influence the industry for decades. The drives were relatively expensive, often costing hundreds of dollars, but the media were cheap and reusable. This created a business model where hardware manufacturers sold drives at slim margins or even losses, making their profits on ongoing media sales. By the early 1990s, floppy disks were everywhere. They were the primary method for installing software, sharing documents, and backing up data. School computer labs were filled with students labeling their homework disks. Offices maintained libraries of software and data on countless floppies. The technology had become so ubiquitous that floppy disk became synonymous with computer storage for an entire generation. But even at the height of their popularity, the limitations of floppy disks were becoming apparent. As software grew more sophisticated, applications began requiring multiple disks for installation. Graphics and multimedia content demanded more storage space than floppies could provide. The rise of computer networks made sharing data over cables more attractive than physically carrying disks. Most critically, the fundamental capacity limit of 1.44 megabytes, which had seemed generous in 1987, was looking increasingly inadequate by 1993. A single high-resolution photograph could fill an entire disk. Complex documents with embedded images might require several disks. Software installations that required users to swap dozens of disks in sequence became exercises in frustration. The industry tried various approaches to extend the floppy disk's lifespan. Companies developed higher capacity versions, 2.88 megabyte disks, zip disks that could hold 100 megabytes, and various proprietary formats. But these solutions faced the classic chicken and egg problem. Users wouldn't adopt new formats without widespread software support, and software developers wouldn't support formats without a large installed base. Meanwhile, other storage technologies were rapidly advancing. Hard drives were becoming cheaper and more reliable. CD-ROM drives were appearing in personal computers, offering 650 megabytes of storage on a single disk. Network connectivity was making it possible to store and share data without physical media at all. The floppy disk era was drawing to a close, but its impact on personal computing was permanent and profound. Floppy disks had taught an entire generation what it meant to own and control their digital data. They had established the metaphors and mental models that we still use today. Files and folders, copying and moving, saving and loading. More than that, they had proven that storage technology could be both powerful and personal. The same principles that made floppy disks successful, portability, affordability, reliability, and ease of use, would drive storage innovation for decades to come. Every storage technology that followed, from hard drives to solid-state drives, would be measured against the standard that floppy disks had set. As we moved into the mid-1990s, it was clear that the future of storage lay elsewhere. But the age of the floppy disk had been more than just a technological phase. It had been the foundation upon which the entire personal computer revolution was built. While floppy disks were revolutionizing how people interacted with their personal computers, another storage technology was quietly evolving in corporate data centers and research laboratories. This technology would eventually become so fundamental to computing that we'd measure a computer's capability by its storage capacity. It would grow from room-sized behemoths costing millions of dollars to pocket-sized devices cheaper than a dinner out. This was the hard disk drive, and its story begins in 1956 with a machine that IBM called RAMAC. RAMAC stood for Random Access Method of Accounting and Control, but the engineers who built it might as well have called it Miracle. The IBM 305 RAMAC system was the first computer to use magnetic disk storage, and it was unlike anything that had come before. Picture a machine the size of 2 refrigerators, weighing over a ton, containing 50 aluminum disks, each 2 feet in diameter, spinning at 1,200 revolutions per minute. The entire system could store 5 megabytes of data, about as much as 3.5 floppy disks would hold 30 years later. 5 megabytes might not sound impressive today, but in 1956, it was revolutionary. For the first time in computing history, you could store large amounts of data and access any part of it almost instantly. Unlike magnetic tape, which required winding through hundreds of feet to find a specific piece of information, RAMAC could move its read/write heads to any location on any disk in less than a second. This was random access storage, the ability to jump directly to any piece of data without reading through everything else first. The implications were staggering. Businesses could now store customer records, inventory data, and financial information in ways that made complex queries and calculations practical. Instead of spending hours searching through filing cabinets or reels of magnetic tape, operators could retrieve specific information in seconds. RAMAC didn't just store data, it made data useful. But RAMAC was expensive, incredibly expensive. The lease price was $3,200 per month in 1956 dollars, equivalent to about $35,000 per month today. That works out to roughly $7,000 per megabyte per month. Only the largest corporations and government agencies could afford such systems, and even then, they were considered major capital investments that required dedicated operators and climate-controlled rooms. The technology behind RAMAC was both elegant and crude by today's standards. The read/write heads didn't actually touch the disk surface. They flew just above it, supported by a cushion of air created by the spinning disks. This flying height was measured in thousandths of an inch, requiring precision manufacturing that pushed the limits of 1950s engineering. If a head crashed into the disk surface, and they often did, it could destroy both the head and the data stored beneath it. Despite these limitations, RAMAC proved that magnetic disk storage was not just possible but practical. Over the next decade, IBM and other companies worked to make disk drives smaller, more reliable, and more affordable. By the late 1960s, disk drives had shrunk from room-sized monsters to desk-sized units, and storage capacities had grown into the hundreds of megabytes. But hard drives remained primarily a technology for large computers and wealthy organizations. The personal computer revolution of the 1970s was built on much simpler storage systems. First cassette tapes, then floppy disks. The idea that individuals might have hard drives in their personal computers seemed as unlikely as having their own mainframe computers. That began to change in 1973, when IBM introduced the 3340 disk drive. Nicknamed Winchester after the famous rifle, the 3340 established many of the principles that would define hard drive technology for the next 50 years. Instead of removable disk packs, the Winchester used sealed units where the disks, heads, and drive mechanism were permanently enclosed in a clean environment. This dramatically improved reliability and allowed for much tighter tolerances between the heads and disk surfaces. The Winchester also introduced the concept of multiple platters in a single drive. Instead of one large disk, it used several smaller disks stacked on a single spindle, with read/write heads accessing both the top and bottom surfaces of each platter. This design allowed for much higher storage density and became the standard architecture that we still use today. More importantly, the Winchester proved that hard drives could be manufactured as standardized, interchangeable components rather than custom-built systems. This standardization would eventually make hard drives cheap enough for personal computers, though that revolution was still more than a decade away. The late 1970s and early 1980s saw rapid improvements in hard drive technology, driven by the growing demands of business computing. Storage capacities doubled every few years, while prices gradually decreased. Drive mechanisms became more reliable, and new manufacturing techniques allowed for higher precision and smaller form factors. But the real breakthrough came in 1980, when a small company called Seagate Technology introduced the ST506, the first hard drive designed specifically for personal computers. At 5.25 inches wide and capable of storing 5 megabytes, the ST506 was tiny compared to the multi-hundred megabyte drives used in many computers, but it was perfect for the emerging personal computer market. The ST506 cost $1,500, expensive for individual users, but within reach of serious computer enthusiasts and small businesses. More importantly, it was designed to work with the same controllers and interfaces used by floppy disk drives, making it relatively easy for computer manufacturers to integrate hard drives into their systems. The impact was immediate and transformative. Personal computer users who had grown frustrated with the limitations of floppy disks suddenly had access to storage capacity that seemed almost unlimited. 5 megabytes could hold thousands of documents, dozens of programs, and extensive databases. For the first time, personal computer users could think of their machines as permanent repositories for their digital lives, rather than just tools for processing information stored on removable media. But perhaps more importantly, hard drives changed how we use computers. With floppy disks, every program and document had to be loaded from external media, which was slow and cumbersome. With hard drives, software could be permanently installed and launched almost instantly. This made computers much more responsive and user-friendly, encouraging people to use them for a wider variety of tasks. The early 1980s saw explosive growth in the hard drive market. Companies like Seagate, Western Digital, and Quantum competed fiercely to offer higher capacities at lower prices. Drive capacities grew from 5 megabytes to 10, then 20, then 40 megabytes. Prices dropped from $300 per megabyte to $100, then $50, then lower still. This rapid improvement was driven by a combination of technological advances and manufacturing improvements. Engineers learned to make read/write heads fly closer to the disk surface, increasing data density. They developed better magnetic materials that could store more information in smaller spaces. They improved manufacturing precision, allowing for tighter tolerances and more reliable operation. But the real revolution came with the introduction of 3.5-inch drives in the mid-1980s. Just as floppy disks had shrunk from 8 inches to 5.25 inches to 3.5 inches, hard drives followed the same path. The smaller form factor allowed computer manufacturers to build more compact systems, while the improved manufacturing techniques enabled higher storage densities and better reliability. By 1987, 3.5-inch hard drives with capacities of 20 to 40 megabytes were becoming standard equipment on personal computers. The IBM PC/AT, introduced in 1984, could be configured with a 20-megabyte hard drive for about $6,000 total. Expensive, but affordable for businesses and serious computer users. The late 1980s and early 1990s saw the hard drive industry enter a period of explosive growth that would continue for decades. Storage capacities doubled roughly every 18 months, following a pattern similar to Moore's law for processors. Meanwhile, prices continued to fall, making hard drives accessible to an ever broader range of users. This period also saw the emergence of new applications that were only possible with large amounts of local storage. Desktop publishing software like PageMaker required tens of megabytes for fonts and graphics. Database applications could store and search through thousands of records. Computer-aided design programs could maintain libraries of complex drawings and models. Perhaps most importantly, hard drives enabled the development of graphical user interfaces like Windows and the Mac OS. These systems required substantial amounts of storage for their visual elements, icons, fonts, backgrounds, and system files. While early versions of these systems could run from floppy disks, they were much more practical and responsive when installed on hard drives. The 1990s brought a new wave of innovations that would define hard drive technology for the next 2 decades. Advances in materials science led to better magnetic media and more sensitive read/write heads. Improved manufacturing processes allowed for smaller components and tighter tolerances. Most importantly, engineers learned to pack multiple gigabytes of storage into the same physical space that had once held mere megabytes. The introduction of IDE, integrated drive electronics, interfaces in the late 1980s had simplified hard drive installation and reduced costs by moving much of the controller electronics onto the drive itself. This was followed by SCSI, Small Computer System Interface, which offered higher performance and the ability to connect multiple drives to a single controller. But the real breakthrough came with the development of what engineers called areal density, the amount of data that could be stored on each square inch of disk surface. Through a combination of better magnetic materials, more precise manufacturing, and advanced read/write head designs, engineers managed to increase areal density by more than 60% per year throughout the 1990s. This improvement was driven by several key innovations. Thin film heads, borrowed from audio tape technology, could read much weaker magnetic signals than their predecessors. Improved servo systems could position heads more precisely over data tracks. Better error correction algorithms could recover data even when the underlying magnetic signal was partially corrupted. By the mid-1990s, hard drives with capacities measured in gigabytes were becoming common. A 1 gigabyte drive, enough storage for about 700 floppy disks, cost less than $1,000. This represented a price-to-capacity ratio improvement of more than 1,000-fold, compared to the early days of personal computer hard drives, just 15 years earlier. The impact on computing was profound. Software developers, no longer constrained by severe storage limitations, began creating applications with rich multimedia content. Operating systems grew more sophisticated, with extensive help systems, sample files, and bundled applications. Users began thinking of their computers as digital libraries, capable of storing thousands of documents, hundreds of programs, and extensive collections of data. The late 1990s brought another wave of innovation as the Internet began driving demand for even larger storage capacities. Web browsers needed space to cache frequently visited pages. Email programs stored increasingly large mailboxes. Digital cameras were beginning to appear, creating demand for storage of high-resolution images. Drive manufacturers responded with increasingly sophisticated technologies. Giant magnetoresistive GMR heads, developed in IBM research laboratories, could detect much smaller magnetic signals than previous designs. Improved disk materials allowed for higher data densities. Better motor and bearing systems enabled drives to spin faster, reducing access times and improving performance. The race for higher capacities led to innovations in drive architecture as well. Engineers learned to pack more platters into the same physical space, and to make those platters thinner while maintaining rigidity. They developed more sophisticated error correction systems that could handle the inevitable imperfections that came with higher data densities. By 2000, drives with tens of gigabytes were commonplace, and the first 100 gigabyte drives were appearing. The price per megabyte had fallen to less than a penny, a reduction of more than 99% from the early days of personal computer hard drives. But the hard drive industry was just getting started. The 2000s would bring even more dramatic improvements as digital media, music, photos, and video began driving consumer demand for massive storage capacities. The industry would learn to manufacture drives with hundreds of gigabytes, then terabytes, of capacity, while continuing to reduce prices and improve reliability. More importantly, hard drives would become the enabling technology for entirely new categories of applications. Digital video editing, which required enormous amounts of storage and fast access speeds, became practical for individual users. Digital music collections replaced physical CDs. Computer games grew increasingly sophisticated, with detailed 3D graphics and extensive audio that demanded gigabytes of storage space. The hard drive had evolved from a room-sized curiosity costing millions of dollars to a desktop component costing less than $100, but offering 1,000,000 times more storage capacity. This improvement, a billion-fold increase in cost-effectiveness over 50 years, represented one of the most dramatic technological advances in human history. But even as hard drives were reaching new heights of capacity and affordability, other storage technologies were beginning to challenge their dominance. Optical storage, in the form of CD-ROMs and later DVDs, offered large capacities and perfect reliability for read-only applications. Flash memory, still expensive and limited in capacity, showed promise for applications where the mechanical complexity of hard drives was a disadvantage. The stage was being set for the next chapter in the storage revolution. But for now, in the early 2000s, the hard drive reigned supreme as the foundation of personal computing. Every computer needed one. Every user depended on one, and the entire digital economy had been built on the assumption that large amounts of reliable, affordable storage would always be available. The hard drive revolution had succeeded beyond the wildest dreams of its pioneers. What had started as an experimental system for storing accounting records had become the memory of the digital age. And the best was yet to come. In 1982, while personal computer users were still wrestling with the limitations of floppy disks and dreaming of affordable hard drives, two Japanese companies were about to revolutionize how the world consumed media. Sony and Philips had spent years developing a new technology that would store audio digitally on a disc read by laser light. They called it the compact disc, and while they designed it for music, they were unknowingly creating the foundation for the next great leap in computer storage. The compact disc was a marvel of precision engineering. Each disc was 120 millimeters in diameter, about the size of a small saucer, and contained a continuous spiral track that, if unwound, would stretch over 3 miles. Along this track, billions of microscopic pits were arranged in precise patterns, representing digital audio data that could be read by a laser beam and converted back into sound with perfect fidelity. But the most remarkable thing about CDs wasn't their technical sophistication, it was their capacity. A single compact disc could hold 650 megabytes of data, equivalent to about 450 floppy disks. This was more storage than most personal computer users had ever seen in one place, and it was read-only, permanent, and virtually indestructible under normal use. The computer industry took notice immediately. Here was a storage medium that could hold enormous amounts of data, was cheap to manufacture in quantity, and could be distributed as easily as vinyl records or cassette tapes. The implications for software distribution were staggering. Instead of shipping programs on dozens of floppy disks, software companies could put their entire product on a single CD. The first CD-ROM drives for personal computers appeared in 1985, just 3 years after the compact disc launched for music. These early drives were expensive, often costing more than $1,000, and relatively slow, but they opened up possibilities that had never existed before. For the first time, software developers could create applications that simply wouldn't fit on floppy disks. The impact was immediate and transformative. Encyclopedia publishers like Grolier and Britannica realized they could put their entire multi-volume reference works on single CDs, complete with search capabilities that would have been impossible with printed books. Microsoft bundled its entire programming development environment, including compilers, libraries, and documentation, onto CD-ROM sets. Software companies began creating applications with extensive help systems, sample files, and multimedia content. But the real revolution came with the emergence of multimedia computing in the late 1980s and early 1990s. CD-ROM's massive capacity made it practical to include high-quality audio, images, and eventually video in computer applications. Educational software companies created interactive encyclopedias with thousands of photographs, hours of audio narration, and video clips. Game developers began producing titles with orchestral soundtracks, full-motion video sequences, and detailed graphics that would have been impossible to distribute on floppy disks. The defining multimedia application of the early CD-ROM era was Microsoft's Encarta Encyclopedia, launched in 1993. Encarta demonstrated everything that made CD-ROM special. It contained the full text of a 29-volume encyclopedia, thousands of photographs and illustrations, hours of audio clips including music and historical speeches, and video sequences showing everything from volcanic eruptions to ballet performances. All of this content, which would have filled dozens of books and hundreds of floppy disks, was contained on a single disk that cost less than $100. Encarta wasn't just a software product. It was a proof of concept for an entirely new category of computing. It showed that computers could be more than just tools for processing text and numbers. They could be multimedia platforms capable of delivering rich, interactive experiences that combine text, images, sound, and video in ways that had never been possible before. The success of multimedia CD-ROM applications drove rapid adoption of CD-ROM drives throughout the 1990s. What had been expensive specialty peripherals in the mid-1980s became standard equipment on personal computers. By 1995, It was difficult to find a new computer that didn't include a CD-ROM drive, and software publishers had largely abandoned floppy disk distribution in favor of CDs. This transition wasn't just about storage capacity. It was about changing the fundamental economics of software distribution. Manufacturing a CD cost less than $1, compared to several dollars for the multiple floppy disks required for large applications. CDs were also more reliable, virtually immune to the magnetic field damage and physical wear that could destroy floppy disks. And they were much more convenient for users, who no longer had to swap dozens of disks during software installation. The late 1990s brought the next evolution in optical storage, the digital versatile disc, or DVD. Developed by a consortium of consumer electronics and computer companies, DVD used the same basic laser reading technology as CD, but with significant improvements in data density. Where CDs used infrared lasers and relatively large pits to store data, DVDs used red lasers with shorter wavelengths, allowing for much smaller pits and tighter track spacing. The result was a dramatic increase in storage capacity. A single-layer DVD could hold 4.7 gigabytes of data, more than 7 times the capacity of a CD-ROM. Dual-layer versions could store up to 8.5 gigabytes on a single disk. This was enough capacity to store feature-length movies with high-quality digital video and audio, opening up entirely new possibilities for both entertainment and computer applications. DVD's impact on computing was immediate and multifaceted. Software developers could create even more ambitious applications, with extensive video content, massive databases, and comprehensive multimedia experiences. Game developers produced titles with hours of full-motion video, detailed 3D environments, and surround sound audio. Reference publishers created increasingly sophisticated interactive products that blurred the line between software and entertainment. But DVD's influence extended beyond just higher storage capacity. The format introduced new levels of interactivity and user control that influenced software design across the industry. DVD menus, with their graphical interfaces and branching navigation, became a model for how complex software could present multiple options to users. The concept of special features, bonus content accessible through menu systems, influenced how software publishers thought about adding value to their products. DVD also established optical storage as a viable medium for data backup and archival. While hard drives were becoming larger and more reliable, they were still mechanical devices susceptible to failure. DVDs offered a way to create permanent, read-only copies of important data that could survive for decades under proper storage conditions. This made them popular for everything from photo archiving to software distribution to long-term data preservation. The early 2000s saw the introduction of writable optical media, which transformed how people thought about optical storage. CDR, recordable, and CDRW, rewritable, drives allowed users to create their own CDs, opening up new possibilities for data backup, file sharing, and content creation. DVD+R and DVD-R formats extended this capability to higher capacities, making it practical to back up entire hard drives or create personal movie collections. Writable optical media democratized content creation in ways that hadn't been possible before. Musicians could record and distribute their own albums. Independent filmmakers could create and distribute their movies. Software developers could distribute their products without going through major publishers. Small businesses could create promotional materials and distribute them widely at very low cost. The impact on culture was profound. The ability to easily copy and share CD-ROMs and DVDs contributed to the rapid spread of software, music, and movies, both legally and illegally. File-sharing networks allowed people to distribute optical disc images across the internet. The phrase, "burn a CD," entered common usage as people began creating their own custom music compilations and data backups. But writable optical media also introduced new challenges. The same technology that allowed legitimate users to back up their data and create custom compilations also made it easy to make unauthorized copies of copyrighted software, music, and movies. The entertainment industry spent years developing copy protection schemes to prevent unauthorized duplication, leading to an ongoing technological arms race between content creators and pirates. Despite these challenges, optical storage continued to evolve. The mid-2000s brought high-definition video formats, which demanded even greater storage capacities. The industry responded with Blu-ray disc technology, which used blue-violet lasers, with even shorter wavelengths than DVD's red lasers. This allowed for much smaller pits and higher data densities, enabling single-layer Blu-ray discs to hold 25 gigabytes of data, with dual-layer versions storing up to 50 gigabytes. Blu-ray represented the pinnacle of optical storage technology for consumer applications. The format could store feature-length movies in high definition with lossless audio, interactive menus, and extensive special features. For computer applications, Blu-ray offered enough capacity to distribute the most demanding software packages on single discs, eliminating the need for multiple DVDs even for the largest applications. But by the time Blu-ray reached maturity in the late 2000s, the computing landscape was changing in ways that would challenge the dominance of optical storage. Internet bandwidth was increasing rapidly, making it practical to download large software packages rather than distribute them on physical media. Cloud storage services were emerging, offering convenient alternatives to local optical storage for backup and archival purposes. More fundamentally, the rise of smartphones and tablets created new categories of computing devices that had no room for optical drives. These devices relied entirely on solid-state storage and internet connectivity, representing a vision of computing that was increasingly independent of physical media. The 2010s saw the beginning of optical storage's decline in consumer computing. Laptop manufacturers began shipping models without optical drives to save space and weight. Software publishers increasingly moved to digital distribution through online stores and download platforms. Even the entertainment industry began embracing streaming services over physical media sales. But optical storage's influence on computing extended far beyond its practical applications. The technology established several principles that would influence storage development for years to come. The idea that storage media could be manufactured cheaply in high volumes and distributed widely became the foundation for flash memory cards and USB drives. The concept of read-only distribution media influenced how software publishers thought about protecting their intellectual property. The multimedia capabilities enabled by high-capacity optical storage shaped user expectations about what computers should be able to do. Perhaps most importantly, optical storage proved that storage technology didn't have to follow a single evolutionary path. While magnetic storage was pursuing higher capacities through mechanical precision and material science, optical storage achieved similar goals through completely different means: laser optics, precision molding, and optical physics. This diversification of storage technologies created a more robust and innovative ecosystem that benefited users through increased competition and technological cross-pollination. The optical storage era also established the importance of industry standards in storage technology. The success of CD, DVD, and Blu-ray formats was largely due to broad industry cooperation in establishing common specifications that ensured compatibility across different manufacturers' drives and media. This lesson would prove crucial as the storage industry moved into the flash memory era, where standards battles and compatibility issues would play major roles in determining which technology succeeded. As we moved into the 2010s, optical storage remained important for specific applications: data archival, software distribution in areas with limited internet connectivity, and high-capacity backup solutions. But its role as the dominant distribution medium for consumer software and entertainment was clearly waning, replaced by digital distribution networks and streaming services. The age of optical storage had been relatively brief compared to the decades-long reigns of magnetic tape and hard drives, but its impact was disproportionately large. In less than 3 decades, optical storage had transformed how software was distributed, enabled the multimedia computing revolution, and established new paradigms for how people interacted with digital content. More than that, optical storage had proven that storage technology could be both high-tech and mass-market, sophisticated and user-friendly, powerful and affordable. These lessons would prove invaluable as the industry prepared for its next great transformation: the rise of solid-state storage and the gradual elimination of moving parts from data storage entirely. By the mid-1990s, computer users were living in a world of contradictions. They had powerful desktop computers with gigabytes of hard drive storage and CD-ROM drives that could access vast libraries of information. But when they needed to move data between computers, from home to office, between different departments, or to share files with colleagues, they were often stuck with the same 1.44 megabyte floppy disks that had been the standard for nearly a decade. This was becoming more than just an inconvenience. It was becoming a real barrier to productivity. As software applications grew more sophisticated, individual files were growing larger. A single PowerPoint presentation with embedded images might fill several floppy disks. Digital photographs from the new generation of digital cameras couldn't fit on floppies at all. Complex spreadsheets and databases required multiple disks, making sharing them a time-consuming and error-prone process. The computer industry recognized this problem and began searching for solutions. What they needed was a storage medium that combined the high capacity of hard drives with the portability of floppy disks. It needed to be reliable enough for critical data, affordable enough for widespread adoption, and convenient enough for everyday use. The first major attempt to solve this problem came from nvme, a company that had been struggling in the competitive storage market for years. In 1994, they introduced a product that would briefly capture the imagination of computer users worldwide: the zip drive. The zip drive was ingenious in its simplicity. It used the same basic magnetic storage technology as hard drives, but packaged it in a removable cartridge, slightly larger than a 3.5-inch floppy disk. Each zip disk could hold 100 megabytes of data, nearly 70 times the capacity of a standard floppy. The drives were relatively fast, much more reliable than floppies, and could be connected to any computer through parallel, SCSI, or later USB interfaces. More importantly, nvme marketed the zip drive brilliantly. They positioned it not as a technical storage solution, but as a lifestyle product for creative professionals and power users. Their advertising showed photographers, graphic designers, and other creative professionals using zip drives to easily transport and share their work. The distinctive blue cartridges became a status symbol in design studios and creative agencies. The zip drive's success was immediate and dramatic. Within 2 years of its introduction, nvme had sold millions of drives and hundreds of millions of disks. The company's stock price soared, and competitors scrambled to develop their own high-capacity removable storage solutions. But the zip drive's success also highlighted the fundamental challenge facing removable storage: the network effect. A storage format was only useful if other people had compatible drives. This created a chicken and egg problem, where users wouldn't adopt a format without widespread compatibility, but manufacturers couldn't achieve widespread compatibility without user adoption. nvme tried to solve this by making zip drives as ubiquitous as possible. They partnered with computer manufacturers to bundle zip drives with new systems. They created external drives that could be shared among multiple computers. They even developed a business model around consumables, selling the drives at low margins while making profits on the high-margin disk cartridges. For a few years, it seemed like the zip drive might become the new standard for removable storage. But success bred complications. The very popularity of zip drives made them a target for cost-conscious competitors who developed cheaper alternatives. More problematically, nvme struggled with quality control as they ramped up production to meet demand. The infamous click of death, a mechanical failure that destroyed both drives and data, became a serious problem that damaged the company's reputation. Meanwhile, other companies were pursuing different approaches to the portable storage problem. SideQuest developed removable hard drive cartridges with even higher capacities, but at much higher prices. Sony introduced the mini disc for computer data storage, leveraging their success in the audio market. Imation created the Super Disc, which could read standard floppy disks while offering 120 megabytes of capacity on special media. But while these companies battled over proprietary removable storage formats, a completely different approach was quietly being developed in laboratories around the world. Instead of trying to create better mechanical storage systems, engineers were working on eliminating moving parts entirely through solid-state storage technology. The breakthrough came with NAND flash memory, a technology that could store data electronically without requiring power to maintain it. Flash memory had been around since the 1980s, but it was expensive and had limited capacity. By the mid-1990s, however, improvements in semiconductor manufacturing were making flash memory increasingly practical for portable storage applications. The first major application of flash memory in portable storage was the memory card market for digital cameras and other portable devices. Companies like SanDisk developed small, lightweight cards that could store dozens of high-resolution photographs. These cards were more reliable than mechanical storage, consumed less power, and could withstand physical shocks that would destroy conventional drives. The memory card market initially fragmented into numerous competing formats: compact flash, smart media, multimedia card, secure digital, memory stick, and others. Each format had different physical dimensions, electrical interfaces, and capabilities, creating confusion for consumers and manufacturers alike. But this fragmentation also drove rapid innovation. Competing manufacturers pushed to develop cards with higher capacities, faster transfer speeds, and lower prices. The market rewarded formats that offered the best combination of performance, reliability, and cost-effectiveness. Compact flash emerged as the early leader for professional applications, offering high capacities and fast transfer speeds in a relatively robust package. The cards were about the size of a thick credit card and used a standard ID interface that made them compatible with many existing systems. Professional photographers and other users who needed maximum performance gravitated toward compact flash, despite its larger size. Secure digital (SD) cards found success in consumer applications by prioritizing small size and broad compatibility. SD cards were about the size of a postage stamp but could store hundreds of megabytes or even gigabytes of data. More importantly, the SD Association worked to establish broad industry support for the format, ensuring compatibility across different manufacturers and device categories. The real revolution in portable storage, however, came with the introduction of USB flash drives in the early 2000s. These devices combined flash memory storage with the universal serial bus interface that was rapidly becoming standard on all personal computers. The result was a storage device that was small, fast, reliable, and universally compatible. The first USB flash drives, introduced around 2000, could store 8 to 32 megabytes of data, not much more than a high-density floppy disk. But they offered several crucial advantages. They were much more reliable than mechanical storage. They worked on any computer with a USB port without requiring special software, and they were small enough to carry on a keychain. More importantly, USB flash drives benefited from the rapid improvement in flash memory technology. Capacities doubled regularly while prices fell, following the same exponential improvement curve that had characterized hard drive development in previous decades. By 2005, USB flash drives with gigabytes of capacity were becoming common and affordable. They offered several times the capacity of zip disks while being smaller, more reliable, and universally compatible. The convenience was unprecedented. You could copy files to a USB drive, unplug it from one computer, walk to another computer, plug it in, and immediately access your data. No special software, no compatibility issues, no mechanical reliability concerns. The impact on how people use computers was immediate and profound. USB flash drives eliminated many of the barriers that had made sharing files between computers difficult. Students could easily transport assignments between home and school computers. Business professionals could carry presentations and documents between offices. IT departments could distribute software updates and diagnostic tools on portable drives. The phrase sneakernet, transferring data by physically carrying storage media, became more practical and widespread than ever before. In many situations, it was faster and more reliable to copy large files to a USB drive and physically transport it than to transfer the same data over network connections, especially with the limited bandwidth available in many offices and homes during the early 2000s. USB flash drives also democratized data portability in ways that previous removable storage technologies had not. Unlike proprietary formats like zip disks, which required special drives that not everyone had, USB ports were universal. This meant that a USB flash drive purchased by one person could be used on virtually any computer, making them practical for widespread file sharing and collaboration. The success of USB flash drives effectively killed the market for higher capacity removable disk formats. Why buy expensive zip cartridges and worry about drive compatibility when you could use a USB drive that was smaller, more reliable, and universally compatible? By 2010, iOmega had discontinued the zip drive, and most other removable disk formats had similarly disappeared from the market. But USB flash drives were just the beginning of the solid-state portable storage revolution. As flash memory technology continued to improve, portable storage devices became increasingly sophisticated. External hard drives began incorporating USB interfaces, offering the convenience of plug-and-play connectivity with the high capacity of conventional hard drives. The introduction of USB 2.0 and later USB 3.0 dramatically improved transfer speeds, making it practical to use external drives, not just for file transport, but as primary storage devices. External drives became popular for backup applications, allowing users to easily create copies of their important data on separate physical devices. The portable storage market also began differentiating into specialized segments. High-capacity external drives targeted users who needed to store large media files or complete system backups. Ultraportable USB drives prioritized small size and convenience for everyday file transport. Rugged drives offered enhanced protection against physical damage for users in demanding environments. Security became an increasingly important consideration as portable storage became more widespread. The same convenience that made USB drives popular for legitimate file sharing also made them attractive for data theft and malware distribution. Manufacturers responded by developing drives with hardware encryption, password protection, and other security features. The rise of smartphones and tablets in the late 2000s created new demands for portable storage. These devices often had limited internal storage, but no standard expansion slots. Manufacturers responded by developing specialized storage solutions: microSD cards small enough to fit in phones, wireless storage devices that could be accessed by multiple mobile devices, and cloud storage services that made local storage less critical. By 2010, the portable storage landscape had been completely transformed from what existed just 15 years earlier. Floppy disks had essentially disappeared from new computers. Zip drives and other proprietary removable formats had been relegated to legacy applications. Instead, users had access to a diverse ecosystem of flash-based storage devices that offered higher capacities, better reliability, and greater convenience than had ever been possible before. But perhaps more importantly, portable storage had evolved from a specialized tool used primarily for backup and file sharing into a fundamental component of how people interacted with their digital lives. USB drives became as common as car keys. Memory cards were essential accessories for digital cameras, smartphones, and other portable devices. External drives enabled new workflows for creative professionals and made comprehensive data backup practical for ordinary users. The convenience revolution enabled by portable solid-state storage also laid the groundwork for the next major transformation in computing: the move toward cloud-based storage and services. As internet connectivity became faster and more reliable, many of the use cases that had driven portable storage adoption began migrating to online services. But the lessons learned during the portable storage era, the importance of universal compatibility, the value of plug-and-play simplicity, and the need for reliable, affordable storage solutions, would continue to influence storage technology development for years to come. The age of mechanical removable storage was over, killed by technologies that were smaller, faster, more reliable, and more convenient. But in proving that portable storage could be both high-capacity and user-friendly, devices like USB flash drives had set the stage for an even more ambitious goal: making storage so fast and reliable that the distinction between local and remote data would begin to disappear entirely. In 1989, a British computer scientist named Tim Berners-Lee was working at CERN, the European Particle Physics Laboratory, when he proposed a radical idea. Scientists around the world were collaborating on complex research projects, But sharing information between different computer systems was cumbersome and often impossible. Berners-Lee envisioned a web of interconnected documents that could be accessed from any computer, anywhere in the world, through a simple addressing system. He called his invention the World Wide Web, and while he was primarily thinking about sharing research documents, he was unknowingly laying the foundation for a fundamental transformation in how we think about data storage. For the first time in computing history, information didn't have to live on the computer where you were working. It could exist anywhere on the network and still be instantly accessible. This concept that storage could be separated from computing would prove to be one of the most revolutionary ideas in the history of information technology. But it would take more than 2 decades for the technology infrastructure and business models to mature enough to make network storage practical for ordinary users. The early Internet of the 1990s was too slow and unreliable to support serious data storage applications. Most users connected through dial-up modems at speeds of 56 kilobits per second or less. Downloading a single high-resolution photograph could take several minutes. The idea of storing your important files in the cloud would have seemed absurd when it took an hour to download a simple software update. But even in those early days, forward-thinking engineers were exploring how network connectivity might change storage. Bulletin board systems allowed users to upload and download files to shared repositories. FTP servers provided centralized storage that could be accessed from multiple computers. Email systems began allowing file attachments, turning electronic mail into a primitive form of distributed storage. The real breakthrough came with the development of network-attached storage, or NAS, in the mid-1990s. NAS devices were essentially dedicated file servers that could be attached directly to local networks, providing centralized storage that multiple computers could access simultaneously. Unlike the mainframe-based file servers of previous decades, NAS devices were designed to be simple enough for small businesses and eventually even home users to deploy and manage. The appeal of NAS was immediately obvious to businesses struggling with the proliferation of personal computers. Instead of each employee maintaining their own files on their own computer, with all the backup, security, and collaboration challenges that entailed, organizations could centralize their data on NAS devices that were professionally managed, regularly backed up, and accessible to everyone who needed them. But NAS also introduced new conceptual challenges that would persist throughout the evolution of network storage. When your files lived on your own computer, you had complete control over them and immediate access to them. When they lived on a network server, you were dependent on network connectivity, server reliability, and the policies set by whoever managed the server. This trade-off between convenience and control would become a recurring theme as storage moved increasingly toward network solutions. The late 1990s brought 2 developments that would accelerate the adoption of network storage: the rapid growth of corporate intranets and the emergence of broadband internet connections. Companies began deploying sophisticated internal networks that could support high-speed access to centralized storage systems. At the same time, cable modems and DSL connections began offering internet speeds that were orders of magnitude faster than dial-up connections. These improvements made it practical to think about storing data not just on local networks, but on remote servers accessed through the internet. The first generation of internet-based storage services began appearing in the late 1990s, offering users the ability to store files on remote servers and access them from any internet-connected computer. Most of these early services were targeted at specific use cases, rather than general-purpose storage. Online backup services allowed users to automatically copy their important files to remote servers for disaster recovery. Web hosting services provided storage for websites and email. Specialized services offered storage for digital photographs, music files, or other specific types of content. But the real transformation began in the early 2000s with the emergence of what would eventually be called cloud storage. The term cloud itself reflected a fundamental shift in thinking about network services. Instead of knowing exactly which server held your data and how to access it, cloud storage abstracted those details away, presenting users with the illusion that their data simply existed in the cloud, somewhere on the internet, accessible from anywhere, without having to worry about the underlying technical infrastructure. Amazon was among the first companies to recognize the broader potential of cloud storage. In 2006, they launched Amazon S3, Simple Storage Service, which allowed developers and businesses to store and retrieve any amount of data from anywhere on the web. S3 wasn't designed for end users. It was a technical service for software developers, but it established many of the principles that would define cloud storage for the next 2 decades. S3 introduced the concept of virtually unlimited storage capacity at prices that scaled with usage. Instead of buying and maintaining your own servers, you could simply pay for the storage you actually used. Instead of worrying about hardware failures and data backup, Amazon handled all the technical complexity behind the scenes. Instead of being limited to accessing your data from specific locations, you could retrieve it from anywhere with an internet connection. The success of S3 demonstrated that there was enormous demand for storage services that eliminated the complexity and cost of managing physical storage infrastructure. Other technology companies quickly followed with their own cloud storage offerings, each targeting different market segments and use cases. But the breakthrough that brought cloud storage to mainstream consumers came in 2007 with the launch of Dropbox. Founded by Drew Houston and Arash Ferdowsi, 2 MIT students who were frustrated by the difficulty of accessing their files from different computers, Dropbox solved the user experience problem that had limited previous cloud storage services. Earlier cloud storage services had required users to understand concepts like uploading, downloading, and web interfaces. Dropbox made cloud storage invisible by integrating it directly into the computer's file system. Users could simply drag files into a special Dropbox folder on their computer, and those files would automatically appear on any other computer where they had installed the Dropbox software. It looked and felt exactly like local storage, but with the magical property that files were automatically synchronized across all of a user's devices. The impact was immediate and transformative. For the first time, ordinary users could easily access their files from any computer without having to think about storage technology at all. Students could work on assignments at school and continue editing them at home without having to remember to copy files to a USB drive. Business professionals could access their presentations and documents from any computer, anywhere in the world. Families could automatically share photo collections across all their devices. Dropbox's success inspired a wave of competition and innovation in consumer cloud storage. Google launched Google Drive, integrating cloud storage with their popular web-based productivity applications. Microsoft developed OneDrive, bundling cloud storage with Windows and Office. Apple created iCloud, making cloud storage a seamless part of the iPhone and Mac user experience. Amazon introduced Cloud Drive for consumers, leveraging their existing S3 infrastructure. Each service differentiated itself through different approaches to the fundamental challenges of cloud storage. Google emphasized integration with web-based applications and powerful search capabilities. Microsoft focused on compatibility with existing Office workflows and enterprise features. Apple prioritized seamless synchronization across their ecosystem of devices. Amazon competed primarily on price and storage capacity. But all of these services shared certain common characteristics that defined the cloud storage era. They offered virtually unlimited storage capacity at prices that continued to decrease over time. They provided automatic synchronization across multiple devices. They included web-based interfaces that allowed access from any internet-connected computer. And they handled all the technical complexity of backup, redundancy, and infrastructure management behind the scenes. The rise of smartphones and tablets accelerated the adoption of cloud storage by creating scenarios where traditional storage approaches simply didn't work. Mobile devices often had limited internal storage and no expansion slots, making cloud storage essential for accessing large collections of documents, photos, and media files. The always-connected nature of mobile devices made cloud storage more practical and reliable than it had ever been on desktop computers. Cloud storage also enabled entirely new categories of applications and services. Photo-sharing services like Instagram relied on cloud storage to allow users to share images instantly across the globe. Collaboration tools like Google Docs used cloud storage, to allow multiple people to edit the same document simultaneously. Streaming services like Spotify and Netflix used cloud storage to deliver media content on demand without requiring users to download and store files locally. But perhaps most importantly, cloud storage began to change how people thought about the relationship between their data and their devices. For decades, the implicit assumption had been that your files lived on your computer, and accessing them required physical access to that specific machine. Cloud storage broke that connection, making data device independent and location independent. This transformation wasn't without challenges and controversies. Moving data to cloud storage meant trusting third-party companies with your most important information. Privacy advocates worried about government surveillance and corporate data mining. Users in areas with poor internet connectivity found cloud storage unreliable or unusable. Businesses worried about losing control over their data and becoming dependent on external service providers. The cloud storage industry responded to these concerns by developing increasingly sophisticated security, privacy, and reliability features. End-to-end encryption became standard, ensuring that even the storage providers couldn't access users' data. Redundant storage across multiple data centers provided unprecedented reliability. Service-level agreements guaranteed specific levels of availability and performance. By 2010, cloud storage had reached a tipping point. Major technology companies were investing billions of dollars in data center infrastructure to support cloud services. Broadband internet had become fast and reliable enough to make cloud storage practical for most users. Smartphones and tablets were creating new demand for device-independent storage solutions. The 2010s saw cloud storage evolve from a novel technology used primarily by early adopters to an essential infrastructure service that billions of people depended on every day. Storage capacities offered by cloud services grew from megabytes to gigabytes to terabytes, while prices continued to fall. Integration with operating systems and applications became so seamless that many users stopped thinking about where their data was physically stored. Cloud storage also enabled the development of new business models and economic structures around data. Software as a service, SaaS, applications could store user data in the cloud, eliminating the need for complex local installations. Platform as a service, PaaS, offerings allowed developers to build applications without worrying about storage infrastructure. Infrastructure as a service, IaaS, solutions provided the foundation for entirely new categories of internet-based businesses. The COVID-19 pandemic of 2020 accelerated cloud storage adoption as remote work and distance learning became widespread. Organizations that had been hesitant to move their data to the cloud found themselves forced to enable remote access to their systems practically overnight. Cloud storage services experienced unprecedented demand as billions of people began working, learning, and socializing from home. But even as cloud storage achieved mainstream adoption, it also highlighted new challenges and trade-offs. Internet outages could make data inaccessible even when the user's device was working perfectly. Subscription costs for multiple cloud services could add up to significant monthly expenses. Vendor lock-in made it difficult to switch between different cloud providers. Regulatory compliance became complex when data might be stored in multiple countries with different privacy laws. The late 2010s and early 2020s also saw the emergence of hybrid storage models that attempted to combine the benefits of local and cloud storage. Edge computing brought cloud storage capabilities closer to users, reducing latency and improving reliability. Personal cloud devices allowed users to create their own private cloud storage systems at home. Distributed storage networks used blockchain and peer-to-peer technologies to create decentralized alternatives to centralized cloud services. As we moved into the 2020s, cloud storage had fundamentally transformed not just how we store data, but how we think about the relationship between information and physical location. The idea that your files had to live on your computer, which had been a basic assumption of computing for its first 50 years, was increasingly obsolete. Instead, data could exist anywhere and be accessible everywhere, limited only by network connectivity and service availability. This transformation set the stage for even more radical changes in storage technology. If data no longer needed to be tied to specific physical locations, then the underlying storage technology could be optimized for different priorities. Cloud providers could focus on maximizing density and minimizing cost per bit, while local devices could prioritize speed and responsiveness over capacity. The result would be a new generation of storage technologies that abandoned the one-size-fits-all approach that had characterized previous decades. Instead of every computer having essentially the same type of storage, different parts of the computing ecosystem began specializing for different roles, leading to innovations that would make storage faster, more reliable, and more efficient than ever before. In 1988, a small Israeli startup called nvme was working on a problem that seemed almost trivial at the time. They were trying to develop a solid-state storage solution for military applications, something that could store data reliably in harsh environments where traditional mechanical hard drives would fail. The military needed storage that could withstand extreme temperatures, violent vibrations, and electromagnetic interference while consuming minimal power and operating silently. Their solution was based on NAND flash memory, a technology that had been developed at Toshiba just a few years earlier. Flash memory could store data electronically without moving parts, making it inherently more rugged than mechanical storage. But in 1988, flash memory was expensive, had limited capacity, and wore out after a relatively small number of write cycles. The idea that it might one day replace hard drives in mainstream computing seemed as fantastical as personal flying cars. nvme's early solid-state drives were more curiosities than practical storage solutions. They offered just a few megabytes of capacity at prices that were hundreds of times higher than equivalent hard drive storage. They were primarily used in specialized military and industrial applications, where reliability was more important than cost or capacity. But the engineers at nvme and other flash memory companies understood something that wouldn't become obvious to the broader technology industry for another 2 decades. The fundamental physics of flash memory were superior to mechanical storage in almost every way except cost and capacity. And in the semiconductor industry, cost and capacity problems had a way of solving themselves through continuous technological improvement. The key insight was that flash memory followed the same exponential improvement curve that had driven the development of processors and computer memory. Every few years, advances in semiconductor manufacturing allowed engineers to pack twice as many memory cells into the same physical space while reducing the cost per bit. This meant that flash memory capacity would grow exponentially while prices fell exponentially, exactly the same pattern that had made personal computers possible in the first place. Throughout the 1990s, flash memory found success in applications where its advantages outweighed its cost disadvantages. Digital cameras used flash memory cards because mechanical storage would be destroyed by the physical shocks of normal camera use. Portable music players relied on flash memory because it consumed less power and could survive being dropped or jostled. Industrial computers used flash-based storage in environments where temperature extremes or vibrations would kill conventional hard drives. Each of these applications pushed flash memory technology forward. Camera manufacturers needed higher capacities to store more high-resolution images. Music player companies wanted faster transfer speeds and lower power consumption. Industrial users demanded better reliability and longer lifespans. The cumulative effect was rapid improvement in flash memory performance across all dimensions. But the real breakthrough came in the early 2000s when several companies began developing flash-based storage specifically designed to replace hard drives in personal computers. The challenge was enormous. Personal computer users expected storage devices to offer hundreds of gigabytes of capacity at prices measured in dollars per gigabyte, not hundreds of dollars per gigabyte. The first generation of consumer solid-state drives appeared around 2003, and they were impressive primarily for their audacity rather than their practicality. These early SSDs offered 32 or 64 gigabytes of capacity at prices of $1,000 to $3,000, roughly 50 times the cost of equivalent hard drive storage. They were purchased mainly by enthusiasts and professionals who valued their performance advantages over cost considerations. But even those expensive early SSDs demonstrated capabilities that hard drives simply couldn't match. Boot times that had taken minutes with hard drives were reduced to seconds with SSDs. Applications that had required careful management of virtual memory and disk caching became instantly responsive. File operations that had involved waiting for mechanical heads to seek across spinning platters became nearly instantaneous. Perhaps more importantly, SSDs were completely silent and generated virtually no heat. For users accustomed to the constant whirring, clicking, and grinding sounds of hard drives, the complete silence of SSD-based computers was almost unsettling. The absence of moving parts also meant that SSDs were immune to the physical shocks that could destroy hard drives, making laptops much more reliable and portable. The performance advantages of SSDs weren't just about raw speed. They were about changing the fundamental character of computing. Hard drives had always been the bottleneck in computer systems, forcing users to carefully manage their data access patterns and wait for mechanical operations to complete. SSDs eliminated that bottleneck, making computers feel more responsive and immediate than they had ever been before. But the high cost of early SSDs limited their adoption to niche markets and early adopters. Mainstream computer users were unwilling to pay premium prices for storage devices that offered less capacity than much cheaper hard drives. The SSD industry needed to achieve dramatic cost reductions while maintaining the performance advantages that justified their existence. The breakthrough came through a combination of manufacturing improvements and architectural innovations. Semiconductor companies like Samsung, Intel, and Toshiba invested billions of dollars in advanced fabrication facilities that could produce flash memory chips with smaller feature sizes and higher densities. At the same time, SSD manufacturers developed more sophisticated controllers that could manage flash memory more efficiently and extend its lifespan. One of the most important innovations was wear leveling, a technique that distributed write operations across all the flash memory cells in an SSD to prevent any single area from wearing out prematurely. Early flash memory devices had been limited by the tendency of frequently written areas to fail after relatively few write cycles. Wear leveling algorithms solved this problem by ensuring that write operations were distributed evenly, dramatically extending the useful life of SSDs. Another crucial development was overprovisioning, the practice of including extra flash memory capacity that wasn't visible to the user but could be used to replace cells that had worn out. This technique, combined with sophisticated error correction algorithms, made modern SSDs more reliable than hard drives, despite the inherent limitations of flash memory technology. The late 2000s saw SSD technology reach a critical tipping point. Capacities had grown to hundreds of gigabytes, while prices had fallen to levels that, while still premium, were within reach of mainstream users who prioritized performance over cost. Major computer manufacturers began offering SSDs as upgrade options, and enthusiasts began retrofitting their existing computers with solid-state storage. The transformation was most dramatic in laptop computers, where the advantages of SSDs were most pronounced. Laptops with SSDs booted faster, ran longer on battery power, and were much more resistant to damage from drops and impacts. The weight savings from eliminating heavy hard drives and their mechanical mechanisms made ultra-portable laptops practical for the first time. Apple was among the first major computer manufacturers to bet heavily on SSD technology. The MacBook Air, introduced in 2008, used SSD storage as one of its key differentiating features, enabling a design that was thinner and lighter than had been possible with traditional hard drives. The instant-on performance and all-day battery life enabled by SSD storage helped establish a new category of ultra-portable computers that would eventually dominate the laptop market. But the real acceleration in SSD adoption came with the introduction of more affordable models that targeted mainstream users rather than performance enthusiasts. Companies like OCZ, Crucial, and Kingston developed SSDs that offered reasonable capacities at prices that, while still higher than hard drives, were within reach of ordinary consumers who wanted to upgrade their existing computers. The upgrade market became a crucial driver of SSD adoption. Unlike other computer components that required technical expertise to install, replacing a hard drive with an SSD was relatively straightforward and offered immediate, dramatic performance improvements. Computer users who had been frustrated by slow boot times and sluggish application performance could transform their systems with a single component upgrade. The performance improvements were so dramatic that they often made old computers feel faster than new computers equipped with traditional hard drives. A 5-year-old laptop with an SSD upgrade could boot faster and feel more responsive than a brand new system with a conventional hard drive. This created a new dynamic where storage technology became a more important factor in system performance than processor speed or memory capacity. The 2010s brought another wave of innovations that further accelerated SSD adoption. The development of smaller form factors like SATA and M.2 allowed SSDs to be integrated more efficiently into laptop and desktop designs. The introduction of new interface standards like SATA 3.0 and nvme eliminated bottlenecks that had prevented earlier SSDs from reaching their full potential performance. NVMe, non-volatile memory express, was particularly transformative because it was designed specifically for solid-state storage, rather than being adapted from interfaces originally developed for mechanical hard drives. NVMe allowed SSDs to communicate directly with the computer's processor through high-speed PCIe connections, eliminating the overhead and limitations of older storage interfaces. The result was a new generation of SSDs that were not just faster than hard drives, but faster than anyone had thought storage devices could be. NVMe SSDs could read data at speeds measured in gigabytes per second rather than megabytes per second, making them hundreds of times faster than traditional hard drives for many operations. These performance improvements enabled new categories of applications that would have been impractical with mechanical storage. Video editing software could work with multiple streams of high-definition video in real time. Database applications could perform complex queries on massive datasets without noticeable delays. Virtual machines could be launched and shut down in seconds rather than minutes. But perhaps more importantly, SSDs changed users' expectations about how computers should behave. Boot times measured in seconds rather than minutes became the new normal. Application launches that happened instantly replaced the familiar experience of waiting for programs to load. File operations that completed immediately eliminated the progress bars and wait times that had been part of computing for decades. The price competition in the SSD market intensified throughout the 2010s as semiconductor manufacturers ramped up production capacity and new players entered the market. Chinese companies like Adata and Silicon Power began offering SSDs at prices that undercut established Western manufacturers. Samsung leveraged its position as both a flash memory manufacturer and SSD producer to offer competitive products across all market segments. By 2015, SSD prices had fallen to the point where they were competitive with hard drives for many applications. While SSDs still cost more per gigabyte than mechanical storage, the performance advantages were so significant that many users were willing to accept smaller capacities in exchange for better responsiveness and reliability. The smartphone revolution also played a crucial role in driving SSD adoption by creating massive demand for NAND flash memory. Every smartphone contained multiple flash memory chips, and the rapidly growing smartphone market provided the volume needed to justify continued investment in flash memory manufacturing. The economies of scale achieved through smartphone production help reduce costs for all flash memory applications, including SSDs. The late 2010s saw SSD technology mature to the point where it began replacing hard drives in mainstream desktop computers, not just laptops. Desktop SSDs offered capacities of multiple terabytes at prices that, while still higher than hard drives, were reasonable for many users. The reliability advantages of SSDs also became more important as computers began storing larger amounts of irreplaceable personal data like photographs, documents, and creative work. Gaming applications became a major driver of SSD adoption as game developers began creating titles that could only achieve their full potential with fast storage. Modern games with detailed 3D environments and high-resolution textures required rapid loading of large amounts of data. SSDs eliminated the loading screens and texture pop-in effects that had been accepted limitations of gaming on mechanical storage. The COVID-19 pandemic of 2020 accelerated SSD adoption as remote work and distance learning increased demand for responsive, reliable computers. Users who had tolerated slow boot times and application launches when computers were used intermittently found these delays much more frustrating when working from home full-time. SSD upgrades became a popular way to improve the performance of existing computers without purchasing entirely new systems. By 2020, SSDs had achieved what had once seemed impossible. They had become the preferred storage technology for most new computer purchases. While hard drives remained important for high-capacity storage applications, SSDs had established themselves as the standard for primary storage, where performance and reliability were priorities. The transformation was particularly dramatic in the laptop market, where SSDs had become virtually universal in new systems. The combination of better performance, longer battery life, and improved reliability made SSDs essential for mobile computing. Even budget laptops began including small SSDs rather than traditional hard drives, accepting reduced capacity in exchange for better user experience. The success of SSDs also demonstrated the power of patient, long-term technological development. What had started as an expensive, low-capacity curiosity in the late 1980s had evolved into a technology that was superior to mechanical storage in virtually every way. The key had been recognizing that the fundamental advantages of solid-state storage, speed, reliability, power efficiency, and silence, would eventually overcome the temporary disadvantages of cost and capacity. As we moved into the 2020s, SSDs were no longer revolutionary technology. They had become the new normal. But their impact extended far beyond just making computers faster. SSDs had changed user expectations about how technology should behave, eliminated many of the reliability concerns that had plagued mechanical storage, and enabled new categories of applications that required instant access to large amounts of data. More importantly, SSDs had proven that storage technology could continue to evolve and improve in fundamental ways. Just as the transition from punch cards to magnetic tape to hard drives had enabled new possibilities in computing, the move to solid-state storage was opening up opportunities that we were only beginning to explore. The age of mechanical storage, which had dominated computing for more than half a century, was finally coming to an end. As we stand in 2025, solid-state drives have achieved what once seemed impossible. They've made mechanical storage obsolete for most computing applications. SSDs are faster, more reliable, more energy efficient, and increasingly cost-competitive with traditional hard drives. But even as we celebrate this triumph of solid-state technology, engineers and scientists around the world are already working on the next revolution in data storage. The challenge they face is both familiar and unprecedented. It's familiar because every generation of storage technology has eventually bumped up against fundamental physical limits that required entirely new approaches to overcome. It's unprecedented because the demands being placed on storage systems today are unlike anything in computing history. Consider the scale of data we're creating. In 2025, humanity generates more than 2.5 quintillion bytes of data every single day. That's more information than was created in all of human history before the year 2000. Internet of Things devices, autonomous vehicles, scientific instruments, social media platforms, and artificial intelligence systems are all generating vast streams of data that need to be stored, processed, and retrieved with unprecedented speed and efficiency. At the same time, we're approaching fundamental physical limits that have constrained storage technology for decades. The transistors in modern flash memory chips are now so small that they're approaching the atomic scale. Engineers are running up against quantum effects and manufacturing tolerances that make it increasingly difficult to shrink storage devices further while maintaining reliability and performance. The response to these challenges is driving innovation in multiple directions simultaneously. Some researchers are pushing existing technologies to their absolute limits through advanced materials science and manufacturing techniques. Others are exploring entirely new physical principles for storing information. Still others are developing systems-level innovations that change how we think about the relationship between storage, computing, and networking. One of the most promising near-term developments is the evolution of NAND flash memory itself. While current flash memory is approaching its physical limits, engineers have developed several techniques to continue improving capacity and performance. 3D NAND technology, which stacks memory cells vertically instead of just shrinking them horizontally, has already enabled dramatic increases in storage density. The latest 3D NAND chips stack more than 100 layers of memory cells, creating storage densities that would have seemed impossible just a few years ago. But even 3D NAND has limits. As engineers stack more layers, they face new challenges with heat dissipation, manufacturing complexity, and electrical interference between layers. The industry is already exploring next-generation flash memory technologies that could overcome these limitations. One promising approach is the development of new types of memory cells that can store more than just the traditional single bit of information. Multi-level cell (MLC) technology already allows each memory cell to store multiple bits by using different voltage levels to represent different combinations of data. Researchers are working on extending this concept even further, potentially allowing single memory cells to store 4, 8, or even more bits of information. But perhaps the most exciting developments in storage technology are happening beyond traditional flash memory. Researchers around the world are exploring fundamentally different approaches to storing information that could offer dramatic advantages in capacity, speed, durability, or energy efficiency. One of the most mature of these technologies is resistive random access memory, or ReRAM. Instead of storing information as electrical charge like flash memory does, ReRAM stores data by changing the electrical resistance of special materials. These resistance changes can be precisely controlled and are non-volatile, meaning they persist even when power is removed. ReRAM offers several potential advantages over flash memory. It can be written and erased much faster, potentially eliminating the performance gap between storage and system memory. It can endure many more write cycles than flash memory, addressing one of the key limitations of current SSD technology. And it can potentially be manufactured at much higher densities, offering more storage capacity in the same physical space. Several major technology companies, including Intel, Samsung, and Micron, have invested heavily in ReRAM research and development. Early commercial products have already appeared in specialized applications, and broader market adoption could begin within the next few years. Another promising technology is phase change memory, or PCM. This approach stores information by changing the physical structure of special materials between crystalline and amorphous states. These structural changes can be induced by heat and are stable over long periods, making PCM suitable for both high-performance computing and long-term data archival. PCM has already found success in specialized applications where its unique characteristics provide clear advantages. Intel and Micron have developed commercial PCM products under the brand name 3DXPoint, which offers performance characteristics that fall between traditional storage and system memory. These devices can serve as ultra-fast storage or as persistent memory that retains data even when power is lost. But researchers are also exploring much more exotic approaches to data storage that could revolutionize how we think about information preservation and retrieval. One of the most fascinating areas of research involves using biological molecules as storage media. DNA, the molecule that stores genetic information in living organisms, has remarkable properties as a data storage medium. It's incredibly dense. A single gram of DNA can theoretically store about 215 petabytes of data, which is roughly equivalent to 215 million gigabytes. It's also extremely durable. Scientists have successfully retrieved genetic information from DNA samples that are thousands of years old. Several research groups and companies are working on practical DNA data storage systems. Microsoft has demonstrated the ability to store and retrieve digital files using synthetic DNA, and they've suggested that DNA storage could become cost-effective for long-term archival applications within the next decade. The process involves converting digital data into DNA sequences, synthesizing the corresponding DNA molecules, and then storing them in controlled environments. DNA storage isn't likely to replace SSDs for everyday computing applications. The read and write processes are currently much too slow for interactive use. But for applications that require extremely long-term storage of large amounts of data, DNA could offer unprecedented density and durability. Another biological approach involves using proteins and other organic molecules to store information. Researchers have demonstrated the ability to encode data in the three-dimensional structure of proteins, potentially creating storage media that are both incredibly dense and environmentally sustainable. Beyond biological storage, researchers are exploring quantum mechanical effects for data storage and processing. Quantum storage systems could potentially offer exponential increases in storage capacity by using quantum superposition to store multiple states simultaneously in single quantum bits or qubits. While practical quantum storage systems are still largely experimental, the principles they're based on could eventually enable storage densities and processing capabilities that are impossible with classical physics. Major technology companies including IBM, Google, and Microsoft are investing heavily in quantum computing research, and quantum storage systems are a natural extension of this work. Perhaps even more exotic are approaches that use the structure of matter itself as a storage medium. Researchers have demonstrated the ability to store information in the atomic structure of materials, creating storage densities that approach theoretical physical limits. These atomic-scale storage systems could potentially store vast amounts of information in incredibly small spaces, though practical implementation remains many years in the future. But the future of storage isn't just about new physical technologies. It's also about new architectural approaches that change how storage systems are designed and deployed. One of the most promising developments is the convergence of storage and computing, often called computational storage or near-data computing. Traditional computer architectures require data to be moved from storage devices to processors for computation, then back to storage for results. This data movement consumes time and energy, and it becomes increasingly problematic as datasets grow larger and computations become more complex. Computational storage addresses this challenge by embedding processing capabilities directly in storage devices, allowing computation to happen where the data already resides. Several companies are developing SSDs with built-in processors that can perform database queries, data compression, encryption, and other operations without requiring data to be transferred to the main system processor. This approach could dramatically improve performance and energy efficiency for data-intensive applications like artificial intelligence, scientific computing, and big data analytics. Another architectural innovation is the development of persistent memory systems that blur the traditional distinction between storage and system memory. These systems use non-volatile memory technologies like 3D XPoint to create memory that's fast enough to serve as system RAM, but persistent enough to serve as storage. Persistent memory could enable new programming models where applications don't need to explicitly save and load data. The memory itself is permanent, so data structures can persist automatically across system reboots and power cycles. This could simplify software development while improving performance and reliability. The networking aspects of storage are also evolving rapidly. Edge computing architectures are placing storage and computing resources closer to where data is generated and consumed, reducing latency and improving responsiveness. Distributed storage systems are using advanced algorithms and networking technologies to create storage pools that span multiple locations while appearing as single, coherent systems to applications. Artificial intelligence is playing an increasingly important role in storage system design and management. AI algorithms can predict which data will be needed next and proactively move it to faster storage tiers. Machine learning models can detect patterns that indicate impending storage device failures, enabling proactive replacement before data loss occurs. AI-driven compression and deduplication algorithms can dramatically reduce the amount of physical storage required for large datasets. But perhaps the most significant trend in storage technology is the increasing specialization of storage systems for different applications and use cases. Instead of the one-size-fits-all approach that characterized earlier storage technologies, the future appears to be heading toward a diverse ecosystem of specialized storage solutions. High-performance computing applications might use ultra-fast persistent memory for immediate access to working data, combined with computational storage for data-intensive operations. Long-term archival systems might use DNA storage for maximum density and durability, with automated systems that can retrieve and convert data back to electronic form when needed. Mobile devices might use advanced flash memory optimized for low power consumption, while cloud data centers might use specialized storage architectures optimized for specific workloads. The environmental impact of storage technology is also becoming a crucial consideration. The energy consumption of global data centers is already significant and growing rapidly. Future storage technologies will need to be not just faster and more capable, but also more energy efficient and environmentally sustainable. Researchers are exploring storage technologies that use less energy for read and write operations, generate less heat, and are manufactured using more sustainable processes. Some approaches, like DNA storage, could potentially be carbon neutral or even carbon negative if the biological materials are sourced sustainably. Looking ahead to the next decade and beyond, several trends seem likely to shape the evolution of storage technology. The convergence of artificial intelligence and storage will create systems that are increasingly autonomous and self-optimizing. The integration of storage and networking will make the physical location of data less relevant while maintaining high performance and reliability. New materials science discoveries will enable storage technologies that are faster, denser, and more durable than anything available today. Advanced manufacturing techniques, including 3D printing of electronic devices and molecular scale assembly, will enable storage systems with unprecedented precision and complexity. But perhaps most importantly, the future of storage will be shaped by applications and use cases that we can only begin to imagine today. Just as the personal computer revolution created demand for floppy disks and the internet revolution drove the development of cloud storage, future technological breakthroughs will create new requirements that push storage technology in unexpected directions. Autonomous vehicles will need storage systems that can instantly access vast databases of map information while recording continuous streams of sensor data. Augmented reality applications will require storage that can deliver immersive 3D environments with zero latency. Brain-computer interfaces might need storage systems that can keep pace with the incredible bandwidth and complexity of human neural activity. Space exploration and colonization will create demands for storage systems that can operate reliably in extreme environments over very long periods. Climate science and environmental monitoring will require storage solutions that can preserve critical data for centuries or even millennia. As we conclude this journey through the evolution of storage technology, it's worth reflecting on how far we've come. We began with punch cards that could hold 80 characters of information, and we now carry devices in our pockets that can store millions of books, thousands of hours of video, and vast databases of information. But more than just increasing capacity, each generation of storage technology has enabled new possibilities and transformed how we interact with information. Floppy disks made personal computing practical. Hard drives enabled graphical user interfaces and complex applications. Optical storage brought multimedia computing to the masses. Flash memory made portable devices practical and enabled the smartphone revolution. Cloud storage freed our data from physical devices and enabled global collaboration. The next generation of storage technologies, whether they're based on exotic materials, biological molecules, quantum effects, or approaches we haven't yet imagined, will undoubtedly enable possibilities that seem as fantastical today as personal computers seemed in the age of punch cards. What remains constant is humanity's relentless drive to store, preserve, and share information more effectively. From the cave paintings of our earliest ancestors to the quantum storage systems of the future, the story of human progress has always been intimately connected to our ability to preserve knowledge and pass it on to future generations. The evolution of storage technology isn't just a technical story. It's a human story about our endless quest to remember, to learn, and to build upon the knowledge of those who came before us. And in that sense, the most exciting chapters of the storage revolution are yet to be written.